Hello everyone. So today we are diving into an essential concept in the theory of programming languages, which is names and bindings. Um, this topic plays a fundamental role in how programming languages work, how variables and functions are managed, and how compilers and interpreters make sense of the code we write. So let's get started. Um, here um, So first of all, a name in programming is an identifier, a label that we use to refer to different entities such as variables, functions, classes, and objects. Just like our own names help us identify individuals, names in programming help us refer to stored data and code elements efficiently. So, um, so here um, now what is bindings? um, just having a name isn't enough. Like, we need to bind it to something meaningful. Like, binding refers to the association between a name and an entity. For example, when we declare a variable in Python like x equal to 10, now here the x is bound to the value 10. Now this binding allows the program to retrieve or manipulate x whenever needed. Now why does this matter? Um, so understanding names and bindings is crucial for managing memory and variables efficiently in different programming languages, and like to determine scope and lifetime of variables in a program, and avoiding naming conflicts and improving code readability through proper naming convention. Okay, so as we move forward in our discussion, let's explore why naming is such a crucial aspect of programming languages. Choosing appropriate names impacts how we manage variables, functions, and objects, ultimately influencing the readability, efficiency, and maintainability of our code. So, here are some key reasons why names matter. So, first of all, organization and readability. So, well chosen names make code more understandable, helping developers quickly grasp what a variable or function does. For example, if we consider these like two variable names, like if we write x equal to 1200, or if we write annual salary equal to 1200, then the second one immediately conveys its meaning, making the code self-explanatory. Uh, like in a group project, let's say in a group project, if someone write x equal to 1200, and if the other person in a group try to edit the code, they won't know what is this for. If you have that annual salary equal to 1200, that the second person will know that this value is for annual salary. So this is how it conveys its meaning. Second is efficient memory management. So names help manage memory allocation efficiently. By using meaningful variable names and proper scoping, programmers can optimize memory usage and avoid unnecessary data storage. Third is encapsulation and modularity. Um, in object oriented programming, naming conventions play a key role in encapsulation and modularity. Classes, methods, and modules should have meaningful names to promote code reuse and maintainability. For instance, naming a class employee details instead of data123 makes its purpose clear. So if you know that employee details, it is the name of the class, so you will know that this class is for to keep the details for employee. If you write data 1 to 3, then you'll know, you won't know that what is this for. uh, Fourth is debugging and error handling. So meaningful names assist in debugging. When errors occur, well named variables and functions help developers quickly locate the issue. Imagine trying to debug a program where every function is named function 1, function 2, function 3. It will be very difficult, or it will be a nightmare. So if you have to check function 1, function 2 and 3 like that to locate the issue, that will be very difficult. But if you have a proper name, then you can just go to that particular function and just find out what's the issue. Okay, now last is code maintainability and scalability. As projects grow, good naming conventions ensure that code remains maintainable and scalable. As I talked about a group project, like if the group grows, if you have a team of 2 members, first of all, and then if it grows and it gets bigger, if you have a group of 5 members, so you have to maintain the code the way you used to maintain before. So if you have a proper name, it will be easier for the growing group members to understand the code easily. When working in teams, like well structured names make it easier for multiple developers to collaborate effectively without confusion. Okay, now that we've discussed why naming is crucial in programming, let's focus on best practices to ensure our names are clear, maintainable, and follow industry standards. Proper naming conventions improve readability, reduce errors, and make collaboration easier in large projects. Okay, so first of all, use descriptive and meaningful names. We'll avoid vague names like X or tempt unless their purpose is obvious. Instead, use names that clearly describe their role in the program. So, for example, if you write total price equal to item price multiply quantity, which is very clear because the the result of the multiplication of the quantity and the item price is the equal of total price. um, but instead, if you use TP equal to IP multiplied by Q, which is very unclear that what does it mean. Second, follow naming convention. um, Different programming languages have established naming conventions like variables, functions, classes. For on variables, if you say snake case or camel case, so snake case is Python and camel case for Java, JavaScript. These are variables you can use. Um, Functions we can use calculate underscore total in Python, or calculate total without underscore in Java. Then on classes, you can have any classes, any name. Third is we'll avoid single letter names unless used in loop counters like I, J, K. These are the names we use for loops. Single letter names can be confusing, so instead opt for meaningful names that clarify intent. Then be consistent. Stick to a uniform naming style throughout your code base. Mixing styles such as using snake case in one place and camel case in another can lead to inconsistencies. That means, like, if you're using one name with underscore and another name without underscore, that is not consistent. If you have similar functions or similar tools which you can have similar style, we can write it using as a underscore, that will be consistent. Then avoid reserved keywords. So using names that clash with built-in language keywords can lead to syntax errors. For example, avoid writing class. Class is already a built-in language keywords. um, if you write my underscore class equal to math, then it will be correct, but if you write class equal to math, it will be incorrect, because class is already a reserved keyword. Okay, last is use meaningful abbreviation. um, when abbreviations are necessary, ensure they are intuitive. For example, if you say num student instead of like ns, that will be more clear, number of student. Okay, all right, so now we'll see, uh, in programming languages we often work with two types of names: reserved words and identifiers. Understanding the distinction between them is crucial to avoid syntax errors and write readable, maintainable code. What are reserved words? Reserved words, also known as keywords, are predefined by the programming language. They have a specific meaning and cannot be used for anything else, such as naming variables or functions. For example, in Python, you cannot write if equal to 5, because that will be a syntax error, because if is a reserved keyword. We use if to have if else condition. Similarly, in Java, you cannot write integer return equal to 10. That will be a compilation error, because return is a reserved keyword. Now, these type of reserved keywords like if, else, while, return, class, def, and many more, depending on the language. Now, what are the user defined names? Um, so these names are identifiers assigned by programmers to variables, functions, classes, and other elements to improve organization and readability. Unlike keywords, these names can be chosen freely as long as they follow language specific rules. So, for example, a valid user defined name will be student underscore name equal to Alice, and then calculate underscore total, which could be a function name. Now, what are the difference between keywords and user defined names? Basically, these keywords are fixed by the language, while identifiers are chosen by the programmers. So, using a keyword as an identifier will result in a syntax error. Okay, now we'll see some valid um, variable names and valid identifiers. So, um, variable names serve as identifiers that help us reference stored values. However, not all names are valid. Different programming languages have specific rules that dictate which identifiers are acceptable. Um, so there are some rules where we have that it should or it must start with a letter or an underscore, but not a digit. So if we have like variable names, um, for example in Python and JavaScript script, if you write student underscore name, which is valid, but if you write one underscore variable equal to Alice, that it is invalid. Second is it cannot be a reserved keyword, the one we just discussed in our previous slide. um, it cannot be a it cannot be a used as variable names if it is reserved keyword. um, like if you excuse me, if you write let function equal to 10, it will give you syntax error because function is a reserved keyword. Okay, then should be descriptive and meaningful. Using a clear, meaningful variable name improves readability and maintainability. Instead of x, use total underscore price equals to x 100 to convey its purpose. Fourth is naming convention vary by language. Like I said before, um, in JavaScript, you can use student name without underscore, and in Python you can write student name with an underscore. So it depends on it varies on language to language. Okay, most programming languages including Python, Java and JavaScript are case sensitive. This means variable name and variable name are treated as different identifiers. That means if you see here in this where V and N is capital and then V and N are small letters, these two variable name are different in Python and Java because these are case sensitive. So you have to be sure that whatever you are writing, you're following the same thing. Okay, now some languages allow Unicode characters, but ASCII is recommended for compatibility. Like certain languages allow Unicode characters in variable names, meaning you can use non-English characters. Um, However, it's best to stick with standard ASCII characters for better cross-platform compatibility. For example, Python supports Unicode, but usage is rare. Like you can write pi equal to 3.14, which is valid but not recommended for readability. Okay, constants and naming rules. Now, in programming, constants are essential for defining values that remain unchanged throughout a program's execution. Unlike variables, constants help improve code stability, prevent accidental modifications, and enhance readability. Now, constants are immutable. Like constants are values that do not change once they are assigned. They ensure that critical values such as mathematical constants or configuration settings remain unchanged during an execution. Second is naming conventions for constants. So, constants are typically written in uppercase letters with underscores separating words. This makes them easily distinguishable from variables. Like if you write max underscore length or pi underscore value in all capital words, then it will you will see that these are constant values which is unchanged. And this convention helps programmers immediately recognize constant values. Why use constants? So, like using constants improves code readability and prevents accidental modifications. By defining important values as constants, we reduce the task or we reduce the risk of unintended changes. Um, so we can declare constants in different languages. Like different languages have specific ways to define constants. Um, First of all, in JavaScript, we can write constant keyword. In Java, you can write final keyword. Then in C and C++, you can have hashtag define, preprocessor directive or constant keyword. Then on Python, no strict constant declaration, but uppercase variable names are used by convention. Okay, now constants help maintain a single source of truth by defining important values in one place. Instead of repeating the same value multiple times in a program, using a constant makes updates easier and reduce errors. Okay, now that we've talked about naming convention, and constants, but what happens when a name is actually assigned to a value or function in a program? That process is called binding. So, understanding how binding work is essential for managing memory, optimizing execution speed, and ensuring consistent variable reference. Now, what is binding? Binding is a process of associating a name with a particular entity, such as a variable, function, or memory address. It essentially determines how and when a variable or function gets connected to its corresponding value or location in memory. Now, what is the role of binding in language processing? First of all, binding plays a key role in how programming languages manage memory. It determines when and where values are stored, which helps optimize resource utilization. Then, the timing of binding, whether early or late, can impact how fast a program executes. So, for instance, some bindings happen at compile time, and some binding occur at runtime, which affect performance. Third is it enables polymorphism in object oriented programming. Binding allows for polymorphism in OOP, where function calls are resolved dynamically. Then last is it ensures that variables and functions can be accessed reliably across different scopes. A variable declared inside a function, for example, may have local scope, while a globally defined variable can be accessed throughout the program. Okay, now that we have understand that what is binding, let's discuss the two main types of binding: early binding and late binding. So, the choice between these two approaches affects performance, flexibility, and how function calls are handled in a program. So basically, early binding is a static binding, and it occurs at compile time. The association between a function or variable and its memory address is determined at compile time. This makes execution faster since everything is pre-solved. Now, because everything is predetermined before execution, early binding improves performance and reduces runtime errors. Then late binding, which happens at runtime, that means that function calls and variable associations are resolved at runtime, allowing more flexibility. Dynamic binding is useful in object-oriented programming where a function call can refer to different methods depending on the object type. Early binding is more efficient but less flexible, and late binding allows for more adaptable code but may introduce performance overhead due to runtime resolution. Choosing between them depends on application needs. In addition to early and late binding, another important concept in programming languages is the strength of binding, whether a language enforces strict type rules or allows flexible type convention, which is weak binding. This impacts how variables interact with different data type and affects program reliability. So first of all, on strong binding, so like languages with strong binding strictly enforce type rules, meaning that variables cannot change types implicitly. This prevents unintended type conversions and makes debugging easier. Um, for example, if you write integer number um, um, equal to 10 and number equal to hello, there will be a compilation error because the type mismatch. Because you said integer, you define the number integer and you're assigning the value string, so there will be a type mismatch. Java does not allow assigning a string to an integer variable due to strong type enforcement. Then on weak binding, languages with weak binding allow implicit type conversion, which can lead to unexpected behavior if not handled carefully. For example, if you write let number, let result, like JavaScript automatically converts the number 10 to a string and concatenates a like 5 instead of adding them mathematically. Okay, now here we can say that strong binding is strictly enforced, um, and it can enhance program readability but may require more explicit type declaration, where weak binding allows for fast prototyping and dynamic interactions but can introduce debugging challenges. The choice depends on the application needs, as I said before, but it prevents unintended type errors, but weak binding can lead to unpredictable behavior. Okay, now we'll see. Now that we have covered different types of binding, let's see how binding is implemented in popular programming languages. First of all, um, okay, now here I'll add the code for you so that it will be easier for you to see an example for all the languages. On C++, if we talk about static binding with function overloading, dynamic binding with virtual functions, like C++ primarily uses static binding by default. Function overloading is an example of early binding. However, dynamic binding is achieved using virtual functions, allowing method calls to be resolved at runtime. On Java, we have method overloading, which is static binding, and polymorphism, which is dynamic binding. Java supports method overloading for static and method overriding for dynamic binding. I'll add the example. Here we have Python. Python is a dynamically typed language, meaning it supports only late binding by default. Since Python does not require explicit type definitions, variable types are determined at runtime, making it highly flexible. Then on JavaScript, which is highly dynamic, allowing function execution and binding to be resolved at runtime. It uses prototype-based inheritance instead of traditional class-based binding. Then on C#, it uses both static and dynamic binding. Okay. Binding in functional programming. Well, functional programming introduces a different way of thinking about binding compared to imperative and object oriented programming. Instead of focusing on mutable states, function programming emphasizes immutable values, lexical scope, and function bindings. Let's see how binding works in this paradigm. Now, first of all, uh, immutable bindings. Like in functional languages, once a variable is bound to a value, it cannot be unchanged. This ensures referential transparency, making programs easier to reason about. Um, Lexical scope. So, functional languages rely on lexical scoping, meaning that the scope of a variable is determined at compile time based on where it is defined. Um, Higher order functions. Functions in functional programming can be treated like values. They can be bound to variables, passed as arguments, and returned from other functions. Okay, closures, which allow functions to retain bindings from their defining environments, even after the outer function has finished execution. Um, Lazy evolution. Some functional languages, such as Haskell, delay binding evolution until the value is actually needed. This improves efficiency by avoiding unnecessary computations. Okay, now as we already know, object oriented programming relies heavily on binding to associate names with objects, methods, and class members. Unlike functional programming, or object oriented programming uses static and dynamic binding in combination with key principles like encapsulation, inheritance, and abstraction to organize and manage code efficiently. So, we'll see some examples here. I'll add those examples so that it will be easier for you. Okay, now explicit versus implicit. Another crucial aspect of binding in programming is type binding, which determines how a variable's type is assigned. There are two main approaches, explicit and implicit. In explicit type binding, the type of a variable is explicitly declared by the programmer at the time of definition. This approach is common in statistically typed languages where type checking occurs at compile time. Where in implicit type binding, the compiler or interpreter automatically infers the type based on the assigned value. This approach is common in dynamically typed languages where variables do not require an explicit declaration. Okay, now we'll try to understand how memory is allocated and bound to variables, which is essential for writing efficient programs. Memory binding determines where and how data is stored during execution. The three main types of memory bindings are stack, heap, and static. Um, First of all, the stack is a region of memory that stores local variables and function call data. It follows a last in first out LIFO order, meaning memory is allocated and deallocated automatically when functions execute and return. This is a fast memory allocation and deallocation process, but it is limited in size and or it automatically managed by the system. Second is heap memory binding. The heap is used for dynamically allocated objects. that persist beyond function calls. Unlike stat memory, heap memory must be manually allocated and deallocated using functions like new, delete in C++ or malloc free in C. It is used for large or long-lived projects or objects. It requires manual memory management in languages like C or C++. It is automatically managed by garbage collection in languages like Python and Java. Then lastly, we have static memory binding, which stores global and static variables which persist for the entire program execution. It retains its value throughout the program, and it is allocated once and persists until the program ends. It's useful for global counters or configuration settings. Okay, name resolution is the process of determining which identifier, like a variable, function, or class, a program refers to during compilation or execution. Different programming languages implement name resolution using distinct scoping mechanisms and resolution strategies. First of all, on C and C++, it is scope-based resolution. C and C++, which uses a scope-based resolution model where names are resolved based on their declared scope, local, global, or namespace. During compilation, function overloading and name mangling allow differentiation between functions with the same name but different parameters. Here, if you look at the global variable, this is the variable. So we use this to access a global variable inside a function, which supports function overloading, and it uses name mangling to differentiate functions, and allows explicit scope resolution using two double colons before the global variable. On Python, it uses LEGB rule, local enclosing global built-in. So LEGB rule means a Python resolves names dynamically at runtime using this rule. So names declared inside a function, then names in the nearest enclosing function scope, then module level variables, and built-in like predefined function like print or something. So here, if you look at here, global x, we are using global x to modify a global variable inside a function. Third is Java. So Java employs both static name resolution and dynamic dispatch. Static resolution applies to overloaded methods, while dynamic dispatch is used for overridden method. If you look at this super dot method name, we are using it to call as a superclass method. Okay, on JavaScript, uses lexical scoping and prototype based resolution to resolve names, where we have this dot property name to access an object's property. Okay, naming conflicts can occur in programming due to multiple functions or variable having the same name. Two common scenarios are name overloading and name shadowing. First of all, name overloading, which is also known as function overloading. This occurs when multiple functions or methods have the same name but different parameters. It allows programmers to define multiple versions of a function with different input arguments. This feature is supported in C++, Java and C Sharp, but not in Python and JavaScript. Functions must differ by parameter types or number of parameters, and overloading is not supported in Python and JavaScript, where function names must be unique. Then name shadowing. This occurs when a local variable or parameter overrides a variable with the same name in an outer scope. This can lead to confusion if not managed properly. Um, it is very common in Java, Python, JavaScript, and C++. Um, Shadowing can cause unexpected behavior if the programmer assumes the outer variable is being modified. In Python, the global keyword allows modifying the outer variables inside a function. Okay, we learned about name overloading and name shadowing. Now we'll see some like while naming variables and functions makes code more readable and structured, it can also lead to conflicts when names are used improperly across different scopes. Let's explore some common issues. First of all, we can have variable shadowing. It happens when a local variable overrides a variable with the same name in an outer scope. This can lead to unexpected behavior where the programmer might think they are modifying a global variable when they are actually modifying a local one. It can lead to confusion when debugging, and it is difficult to track changes across different scopes. Ambiguous function overloading. In statically typed languages like C++ and Java, improper function overloading can create ambiguity where the compiler cannot determine which function to call, which can lead to compiler errors due to unclear function resolution. Then name clashes in global scope. If two modules or libraries define the same variable or function name, conflicts arise, especially in languages without strict name spacing. This is common in C and JavaScript, where multiple libraries might define the same function. Unexpected function overriding, which is the impact of this, and you will have difficulties integrating multiple libraries. Then accidental global modification, like modifying a global variable unintentionally inside a function, can lead to unexpected results. Okay, now aliases and renaming help improve code readability. So these are some techniques which is widely used in variable references, function imports, and type definitions. So aliases allows multiple names to refer to the same variable, function, or module. This is useful for improving readability or adapting naming conventions. Like changes made to the alias affect the original object. So it's useful when working with large data structures, but requires careful management. Renaming during imports helps avoid name conflicts and improves clarity, especially when working with libraries. Then pointer and reference aliases in C++, which allows multiple references to the same memory address. Then lastly, type aliasing, which allows programmers to define alternative names for existing data types, improving code readability. Okay, Now see polymorphism and binding. Um, so this is a static binding and compile time polymorphism, and then dynamic binding and runtime polymorphism. So first of all, it happens when functions or method calls are resolved at compile time. This is commonly achieved through method overloading and operator overloading. So this is an example, and that is another example for dynamic binding and runtime polymorphism, which is commonly achieved through method overriding, where the subclass provides a specific implementation of a method defined in its parent class. Okay. Um, so we'll just see on method overloading again, which occurs when multiple methods have the same name but different parameter types or numbers of parameters. The compiler determines which method to call based on the method signature, leading to early binding. And this improves performance since the method resolution is done before execution. And this is the example of a method. So we have a class math operations. So the compiler determines the correct method based on the data types of the argument, and this decision is made at compile time, meaning no runtime overhead. So let's see some real world examples of name binding. First of all, in web development, in JavaScript, event listeners and functions are dynamically bound at runtime. This allows developers to modify behavior dynamically without requiring recompilation. Database queries. SQL prepared statements use binding variables to optimize performance and prevent SQL injection. Mobile app development. Swift enforces type binding to ensure safety while maintaining flexibility. Type inference allows developers to write concise and readable code. And lastly, game development. So in game engines like Unreal Engine, late binding is used to override base class methods dynamically. This enables runtime polymorphism, allowing objects to behave differently depending on their subclass. Okay, now we'll discuss two common binding errors, unbound and overriding. So, um, unbound error, which occurs when a variable is used before being assigned a value. It is common in dynamically typed languages like Python and JavaScript, where variable declaration is not mandatory. Then, on overriding static binding, this happens when a method is expected to use dynamic binding, runtime polymorphism, but instead it uses statistically bound due to a missing virtual keyword in C++. Okay, so here are some debugging techniques. Well, you can have print statements and logging, which helps track variable bindings. Static code analysis, like tools like PyLint, ESLint, and Clang Static Analyzer help detect early binding issues. Then we can use some debuggers like GDB for C++, PyCharm debugger for Python, Chrome developer tools for JavaScript. Then type annotations, like it helps avoid binding errors in dynamically typed languages. Okay, now that's all for today's lecture. If you have any question or concern, you can email me or please let me know. I will post those example codes for different bindings and for different languages. And if you need anything else, you can email me so that I can also provide those resources. Thank you.